This video is about the absolute value parent function. Okay, we're going to talk about the absolute value parent function, and that is on the screen right here. It is f of x equals absolute value of x. Pretty straightforward. So we're going to be looking at different transformations of this parent function. So let's take a look at a, g of x. What I'm going to do is I'm going to pick some points, and we're going to plot them and kind of see what happens. So our first one is absolute value of x plus 1. So I'm going to do the positives first. So let's see here. 0 plus 1, 0. 1 plus 1, 2. And then 2 plus 1, 3. We'll do 3 points per side. Let's do the other side. So negative 1 becomes positive 2. And negative 2 becomes positive 3. And here we go. All right, so this would be a vertical transformation. And this plus or minus on the outside, its value is k. So I'm going to put a k over here for our k value. Let's look at b. That's the absolute value of x minus 2. So if I take 0 minus 2, we're going to go negative 2. 1 minus 2, negative 1. And 2 minus 1, let's see, 2 minus 1 will be 1. Oh, I mean minus 2. Jeez. 2 minus 2 is 0. We're going to do the same on the other side. 1 minus 2 is negative 1. 2 minus 2 is 0. And I apologize, I'm not pulling my ruler out for this, so bear with me while I try to make straight lines here on my tablet. So we end up with this. Also, this is a vertical transformation. So I'm going to call this one a vertical translation. Which is what I should have wrote for the other one too. We want to be proper with our terms. And this value again is going to be k. So k is what shifts our graph up and down. It's the plus or minus outside the bars. So let's take a look at c. K of x is 3 times the absolute value of x. So if the absolute value of x is 0, 3 times 0, nothing's really going to change here. 0, 0. Let's say I put a 1 in there. So 3 times 1 is going to be 3. So 1, 3. We can do 2 times 3. That's kind of off the scale, so I'm not going to do that one. We'll do negative 1 times 3. That would be 3. Absolute value, negative 1, positive 1 times 3. And as you can see, this is a lot sharper. So what I'm going to do is I'm going to put a regular absolute value on here, just so you can see the difference between k of x and what the parent function looks like. So this is a vertical stretch. The number multiplied is a vertical stretch. So this is a vertical vertical stretch by a factor of 3. So you can see it's almost like I took the blue part and I pulled them up. That's why it's called a vertical stretch. If you really want to, I guess you could also refer to it as horizontal compression. But technically, this is what we would call a vertical stretch. And this value, that 3, would be a. So the a value is on the outside that we're multiplying it by, and that's going to make it generally going to do this to it. And if it's a fraction, it's going to make it be kind of fatter. It'll be a horizontal compression. I mean, a vertical compression. If we look at D, this one's a little bit weird. This one's tricky. So it takes the absolute value, and we're going to plot whatever the opposite is. So opposite of 0, still 0. So if I put in a 1, I get out a 1. The opposite of 1 would be negative 1. Same goes for 2. Negative 1, same thing happens. And then negative 2, same thing happens. and we end up with our function doing this. Basically, that negative flips it over on the x-axis. So recall our parent function. Let me go ahead and graph that too, just for good measure. Our parent function is the other way, the v going up. And then in this case, that negative is going to flip it over and make that v open downwards. So this would be a reflection on the x-axis. Okay. So what we're going to do next is talk about the horizontal shift. I go by the principle here that insiders lie. And basically what that means is that whatever is inside this absolute value bar, we're going to go the opposite direction than it looks like. So for this one, it says -4, and you would think that means left 4, but it really means right 4. So I'm going to go ahead and plot that 1, 2, 3, 4 over. And then I'm going to do my parent function. And we're going to double check it using some logic here. So let's pick some points. So if I picked 4, 4 minus 4 is 0, our intercept. If I picked 5, 5 minus 4 is 1, which is this point right here. If I said 3, 3 minus 4 is -1, absolute value -1, +1, and that's that point right there. So you can see how this plays out. So the same thing is going to work for the next one. So x plus 5. And insider's lie, that really means we're going to shift it left 5 right here. And again, -5 plus 5 is 0. So that's going to be our intercept. We can check. So -6 plus 5, that'd be -1. Absolute value will give us the 1. If we say -4 plus 5, that'll be 1. And so it works the same way with our parent function shifted over. These, I think, for me, are my personal. I like these the most because they're the least amount of work. Let's take a look at number 7. We're going to start by graphing the parent function. Easy enough. I'm going to go ahead and do that in blue, since that seems to be what I keep doing. And again, I apologize. My lines aren't the straightest, but I'm working on a tablet. And then it says we're going to graph the function of the absolute value of 2x. Okay, so let's go ahead and check our values here. So if I say x is 0, 2 times 0 is 0, easy squeezy. If I say it's 1, 2 times 1 is 2. So 1, 2. If I say 2, 2 times 2 is 4, so 2, 1, 2, 3, 4. I'm going to go the other way as well. This should be mirrored over that vertex, but -1 times 2 is -2, and the absolute value of that is +2. 2 times 2 is -2 times 2 is -4. Absolute value of -4 is +4. So we're going to go ahead and graph that. All right, so let's go ahead and describe this graph. This looks to me like a horizontal shrink. So that's what I'm going to call it. Horizontal shrink by a factor of 1/2. By 1/2. You could also call this a horizontal compression, or technically you could call it a vertical stretch. It's really up to you. I prefer to always refer to A values as the vertical stretch or the vertical compression, and this value inside as the horizontal shrink or horizontal stretch. That's really a matter of semantics. So let's take a look at number 8. Use the results from item 7 to predict how the graph h of x equals 1/2, absolute value of 1/2 x, is transformed from the graph of the parent function. Well, let's use some logic here. If 2x if the 2 on the inside did a horizontal shrink, then I would expect the fraction on the inside would do the opposite of a whole number and give us a horizontal stretch. So let's see if that's the case. I'm going to go ahead and graph the parent function so we have a frame of reference real fast. So here's our absolute value function. Okay, and let's do this logically. So I'm going to pick 0. 1/2 times 0 isn't really make a difference. So we're still going to start at 1/2 or at 0. Let's do 1. 1/2 of 1 is 1/2. So 1, 1/2. 1/2 of 2 is 1. And you can kind of see where this is going. So 1/2 of -1, absolute value, it's -1/2. Absolute value makes it a positive half. If we did -2, that's going to be a -1, and absolute value -1, positive 1. So as you can see, our graph is a little more squat here. And this was a horizontal stretch. The fraction is the stretch. This is a horizontal stretch. Horizontal stretch. And it is by a factor of 2. And so it's by the kind of the opposite of what you would think it is. Let's finish up by talking about kind of the best practice for graphing an absolute value function that has more than one thing going on. So what I like to do, and what these directions basically are, is to find the vertex and follow that up by your vertical or horizontal stretch. So let's scroll down and take a look at doing some examples. So let's look at A. What I'm going to do first is figure out where my vertex is. So my H and K, right? It says I'm going to push it up 2 and right 1, or right 1 and up 2, whichever order you prefer. So I'm going to say right 1, up 1, 2. So I know that's going to be my vertex. Okay. I'm going to look at my multiplied value. It's the negative, so I know it's just going to open upside down. So if you are going fast, you can sketch it out just as the parent function like this. This one's not too hard. We can also plug some numbers in. So let's try maybe 0. 0 minus 1 is -1. The absolute value of that is positive 1. This negative flips that positive 1 back to a -1, and -1 plus 2 is 1. So there's our point here. If we had x is 1, 1 minus 1 is 0. Opposite of 0 is still 0. 0 plus 2 is 2. And if we did 2, 2 minus 1 is 1. Absolute value of 1 is 1. The opposite of that, because of this negative, is -1. And -1 plus 2 is back to positive 1. So this is definitely the correct graph. Okay, so for B, I'm going to start off by finding my vertex, which here says left 1, insider's line, and down 3. So left 1, down 1, 2, 3. Okay. Now, a little secret to this value on the outside, this A value, is that it is really kind of the slope of the lines that are coming out of that vertex. So it says 4, so my slope is 4 over 1. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. Now, before I commit to this, let's double check the values. So when x is 0, let's do that one first. 0 plus 1 is 1. 1 times 4 is 4. 4 minus 3 is 1. So that point checks out so far. The other one over here is -2. So -2 plus 1 is -1. The opposite of -1 is 1. 1 times 4 is 4, and 4 minus 3 is 1. So we're definitely on the right path here. We can do the next one, which would be x equals 1. 1, 2, 3, 4 over 1. And let's see if that works. So when x is 1, 1 plus 1 is 2. 2 times 4 is 8. That's 8, 7, 6, 5. And he's at 1, 2, 3, 4, 5. So I'm just going to mirror that on the other side. And I don't know if I can draw that line straight, but I'm going to try. There we go. And there we go. Now, if you are ever in doubt, I would always recommend making yourself a table of values, or doing what I did, taking your vertex as a reference point and then choosing a point to the right of it and putting it in your equation and seeing what you get, taking a point to the left of it, putting it in the equation and seeing what you get. It might be a little bit faster than table of values, and it's always great to check your work if you're unsure.